All right, so this section is titled Integrals in Action. It comes from section 6.2 in your textbook, which is Applications of Antiderivatives. I want to remind you of a few things after we read this slide, and that has to do with how we find basic antiderivatives, so you're going to help me with that. But here's the setup. Imagine 50 years from now, you've led a good life, you worked really hard, you tried to save when you could, but as you near retirement, you find yourself wondering, will I have enough to retire? Is there some way I could have done better? How could I have projected better? What might your 70-ish year old self tell your 20-ish year old self today? That's the premise of what we're going to look at, is how to predict and imagine what that could work out to be better in your future. Okay, so these are some basic antiderivatives, if you'll remember. So we've just taken a test on this. You guys know these. The antiderivative of a constant is the constant times x. The antiderivative of the power is x to the n over n plus 1. When that n happens to be -1, looks like 1 over x, we get the natural log showing up. The antiderivative of e to the x is e to the x. Of e to the ax is e to the x over a. And of b to the x is b to the x over ln b. Okay, so all those should seem super familiar to you. All of them have plus c's at the end, of course, as well. These down here talk about what happens when you have a constant and what happens when you have a sum and difference. So if you have a constant, the constant doesn't affect the antiderivative. It's just the antiderivative of the part with the variable in it. If you have sums and differences, then we just separate them and we treat each of them individually the same way we would have before. So as we're taking a look at this, I want you guys, oh, hang on just a second. We'll delete this out and let you do it. I want you guys to take a look at this one and find out with me what the antiderivative of this. So somebody talk to me. What is the antiderivative as we go? Tell me what we have first. 7x. So somebody else for the next one. X to the 8th over 8. What's next? Yep, 7e to the x. So we're on this one. Audience participation time. Help me out. E to the 7x over 7. And then our last one here at the end. Yep, 1/7, and then the natural log, and then we have to have the absolute value of x. And what am I missing? Plus c. All right, so some basic antiderivatives, just a review of that because we're going to be using them in some of the more extensive questions further on. Also a reminder of the fundamental theorem of calculus. We talk about this in this class, but we talk about it where we are embedded inside of the section about average value, right, where we subtract the two values that happen on your test that you just got back as well. So we look at the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. All right, so we're going to evaluate this integral or antiderivative in that same fashion. So, of course, the first thing that we need to do is to take the antiderivative of 3x to the 4th. What's that? 3x to the 5th, and then over 5. And what about the second piece? What do you get, Mickey?
5e and over 0.4.
Yes, that's right. We don't have to do a plus c because we're evaluating it at the numbers that are given 3 and 0. So what we've done in class, of course, is we've let our calculator evaluate these, but what we're doing is we're taking that number 3 and plugging it in, and then we subtract off what happens when we plug in the number 0. So grab your calculators for me. You can evaluate this and plug in 3, evaluate it to plug in 0. We want to know what the difference is between the two. Are we getting close? Anybody have a value yet? What do you have, Mickey? How do you know?
I mean, I don't know if it's the same as the rest.
Correct. What do you have, though?
116.
Do they have any decimal places?
Yes. 0.79.
Okay.
8.
Oh, 798. Okay. Did anybody else get that same value? Did anybody get a value at all? You guys know the more you engage, the quicker the class goes, and then we can leave.
I'd say that.
Thank you. Did you really, or are you just saying that to move us along? You're just saying it. Okay. You're right. It is, Mickey, the right answer. That's what mine has written down, too. Engage with me, guys. Come on. Play along. All right? Yeah, it is 116.798. Remember, there's a couple of ways that you can put this in your calculator. It is important to remember. You can actually take the original piece that you're given, and you can use Math 7, right? Or 9, sorry, Math 9. And Math 9 allows you to actually plug in 3 and plug in 0 and find it with even without finding the antiderivative. Or you can take the antiderivative and you can use like the table or the y1 features, and you can plug the 3 and the 0 in independently. So we are going to be using both of these two examples as our general examples over here, this one and this one, to do some different calculations for answering the questions about retirement. All right, so this is actually new information. You've never seen this before. This is called future value of a continuous income stream. So this is in 6.2 in your book. It talks about how you estimate your future value of an investment, knowing certain pieces of information. So it says, suppose that an income stream flows continuous into an interest-bearing account at a rate R of T dollars per year, where T is measured in years. The account earns interest at an annual rate of 100% compounded continuously. The future value at the end of capital T years is written down here below. So this is future value. You'll notice that notation you've seen before, right? 0 to some number. We don't know what that number is, but we're going to use the assumption later on that it's our retirement years that we've spent saving for retirement. R of T is how the money is going into the account. We're going to play with this a little bit. The interest rate, the little r right here, is our interest rate for our account, okay? So usually when you work with a financial advisor, if you haven't had an opportunity to talk with some of those things, they can tell you, for example, how a fund, a specific mutual fund or stock fund, has done over the past years, and you can use that as the interest rate that it's talking about. And this capital T right here is the number of years you'd be investing for, and the lowercase t is the time as it passes, okay? So we're going to use this sort of setup with a bit of information about things specifically for our question. You're 20-ish, right? You at 20. Every week you spend $5 at the vending machine. It's probably a lot more than that, or something like that. Maybe it's at Sonic, or maybe it's at Starbucks, or something like that, right? $5. You know it's a waste of money, but really what else can you do with $5? What if you invested it? Would it matter? Would it amount to anything? What if you invested $10 a week instead? How much more would you have at retirement? So we're going to take those assumptions, first the $5 a week. So if you'd invested $5 a week for a year, how much would you have at the end of the year? What would you have to do to find that?
365.
Close, that's $5 a day. We're doing $5 a week. 52. So we have $5, right? And we have 52 weeks. And if you did 5 times 52, what do you get? Grab a calculator. What do you get? 260. Yes, sir. 260. That's not very much money in the grand scheme of things for an entire year, but that's $260, right? This is your R of T equation. So we have found for this premise that we're starting with that R of T is equal to 260. We invest 260 a year, that's it. Not changing it for the next year, nothing, just 260 a year. Let's move on. So if we invest the 260 a year, we are going to talk a little bit. Do you guys know who Dave Ramsey is? A few nodding heads. So Dave Ramsey is a big part of my history at this point. So we we do Dave Ramsey stuff. I would strongly encourage you, if you're not familiar with him, to look him up and listen to some of his stuff. He's actually, oddly enough, a radio talk show host, but he's a financial radio talk show host, an author and speaker and other things. So according to financial guru Dave Ramsey, the stock market is still the best place to invest your money. The long-term track record for mutual funds is good, about 14%. We have funds that are far higher than that in the recent history. So if you decide to follow Dave's advice and you invest in a mutual fund with a solid track record of 14%, then this is the R in your future value equation. So R is 0.14 if you turn it into a decimal. Okay? So we're actually trying to create this, all the details, and that's what we're identifying at this point. Okay, we've created now so that we've found R of t and we've found the little r. That's where we are so far. As you project into the future, you plan to retire at 70. Okay, we're pretending again that you're 20. You're retiring at 70, which means you will invest for how long?
In weeks.
In years. How many years? 50, right? Yeah. You're 70, 20, that's 50 years. That's your t value. The capital T would be 50 years if you go with that premise. Okay? If you're younger or if you retire later or whatever, all those things can be changed. We're just going to go with that for the moment. Okay? Those pieces of information, those three pieces of information, actually create for us that future value equation. So it was an integral. It went from 0 to the capital T value, which we found was 50. R of t, my equation, how much I'm investing yearly, we said was $260. We have our E. It's raised to the little r interest rate, 0.14, times capital T, that was my 50, minus my lowercase t dt. Those are the details, all just stuck into the equation, okay? The question then is, how much do we have in 50 years? So we're going to actually do this particular calculus problem. It's a little different than the ones we've done, but not very different. So let me actually show you how it works. So we have that 0 to 50. I'm actually going to multiply this exponent out since there's a parenthesis in there. So this is 260 e to the, so let's see, I've got 0.14 times 50, that's actually 7, minus 0.14t dt. Okay, so far so good? Okay, so this, while much simpler, actually is a lot like the last problem that we did, at least a component of it, where we actually have a piece right here that is, not the last problem we did, it was one of the middle ones, I apologize, where we have this piece right here that's not just x. There's other stuff in that exponent. What that tells us is we have to do u substitution for this problem. It's not a hard u substitution, but we do have it. So our u value is actually 7 minus 0.14t, right? And if I were to take the derivative, it would actually give you like the negative 0.14. That's what it would be. And you can see that that's not in the problem over here, right? So we have to put it over there by dividing. So in our problem now, we have the integral. We'll leave the 0 and the 50 off for the moment. We have the 260. We're dividing by the 0.14. And now we have e to the u du. E to the u is a wonderful thing to take a derivative of. Well, that's a true statement, but that's not what I meant to say. A wonderful thing to take an antiderivative of, because he's his own best friend, right? You take a derivative, you take an antiderivative, it doesn't change. So the 260 and the 0.14 stay the same. And the antiderivative of e to the u is e to the u. I don't need the plus c because in a moment here I'm going to be evaluating this anyway. Let me shrink this tiny bit so I have more room to work. I need this to be evaluated where the u value is the 7 minus 0.14t. And it's supposed to go from 50 down to 0. Is that all right? Yep.
When you divide by the 0.14, does it not have to be negative?
I left it off. Yes, it does. Thank you for fixing that for me. We'll get that in there. You bet. So we are going to evaluate this like we done in the last problem, where we find the value at 50 minus the value at 0, and we let our calculator do it simply because it's a calculation that it's simple to do with the calculator. And if you do that, what will you end up with? You okay, Thomas?
He was asking when we had to send it from.
Oh, okay. I distributed. Yeah. Right here. Does anybody get a value? It's a big value. It's very exciting. What'd you get?
It's negative.
Shouldn't be negative.
Okay.
Mm-mm. Remember, you're welcome to put this into y1 and then do math 9. Math 9 at 50 and 0. So what'd you get? Tell me your numbers, Kendrick.
2, 0, 3, 4, 7, 4, 7, 1, 2, 4.
Okay, and we'll go to 9 because we're talking money, so we'll do 2 decimal places. So there's a comma and there's a comma. That number looks suspiciously like $2 million. Nobody's excited? $2 million? By giving up $5 a week? I mean, like, let's be real. Even if you're half wrong, you're still a millionaire, right? This is a lot of money. That is a lot of money. All because of the way that compounding of interest is actually working. So not only that, but take a look here. So, hang on. I don't think I got that in there. This is what I meant to do. I don't know what that's supposed to be. On a side note, the amount we contributed each year was $260, right? That's what it was. We did it $260 a year for 50 years. So somebody multiply that for me real quick. So what's $260 a year for 50 years?
13,000.
13,000. So we actually only put in $13,000 of our money, and we end up at the end with $2,034,000. If I got the number right from the previous screen. Yep, $747.29. We invested $13,000 over 50 years, and we are ending up with $2 million. That's kind of crazy. It is, right? So, a little bit on the technology here. As you're trying to describe this to your parents, they give you vacant stares and the words calculus and antiderivative surface into your conversation. So you simplify things and decide to use a calculator to show the above results, just to assure your parents there's no funny business going on with your math. After all, the calculator's always right. So this is actually what you guys were already doing, right? I had you doing this math 9 already. So we went through, we can put in our original antiderivative. This is just to remind you how we were doing it written out. You have your y1 equation, it's x, you put your lower number, that was our 0, this is our 50 as our values in there. Math 9, we have y1 is underneath y bars, of course, all that good stuff. And of course, it gives you the same value that you would do if you got it by hand and your parents doubted you, which is still $2,034,747.29. So that's what happens if you invest $5 a week, right? So we're going to change the premise slightly and decide that you're like, ooh, that's pretty cool, but I could probably do better than $5 a week. I mean, really, $5 a week, that's just my one trip to Starbucks, right? Maybe I'll go and shoot for $10 a week. Let's see what happens if I have $10 a week. Well, what does R of T become? Well, R of T, remember, is how much I am investing per year. So if I'm investing $10 a week and I have 52 weeks a year, what am I going to be investing in total in a year on this scenario? $520. So my future value equation ends up going still 0 to 50, right? It's still got the R of t, but now that R of t is 520. And it's still e to the same values I had before. I'll write it out the way I had, 7 minus 0.14t dt. And we'll let your calculator just do all of it, where we're not going to do it by hand on this one at all. So we put it in our calculator, so all of this goes into y1, right? And then you use Math 9. Depending on your calculator, yours might pull up this beautiful scripty thing where you put in the 0, you put in the 50, you put in the y1, and you put in dx. Or it might pull up fnint, and you put in a y1, you put in an x, and you put in a 0, and you put in a 50. Depends on the operating system. I've got one of each of the calculators doing each of those things. Either way that you do it, depending on your version of your calculator, you should get the same amount. What do you get?
$4 million.
$4 million.
I mean, 4,069.
Uh-huh, keep going.
494.
Yep.
0.58.
Yep. I have 5.9, I think, if around. It suspiciously looks like twice as much. That should make sense. Why should it be twice as much?
Investing double.
You invested double, right? So that makes sense, right? You invested double, it was twice as much. So that's one thing that you can change when you're talking about investment. You can change how much you're inputting. So now, instead of the $13,000 invested, you invested $26,000. Instead of $2 million at the end, you're at $4 million in the end. That's one of the constraints that we can change, how much we invested. But there's other constraints that we can change as well. We can also change the interest rate. And that's a little bit more interesting. So instead of 14%, we're going to do this problem again, but we're going to do it with 16%. It's just a 2% interest rate change. Like, that's not significant. Seems like it's very, very small. In fact, we're going to do it the same way we did before originally with the $5 a week. So we're going to compare it to what we did at our very first question with $5 a week. So our equation would go from 0 to 50 still. It would still be the $260. But instead of the 0.14, it's 0.16. And then it's 50 minus t dt. Or if you want to rewrite this piece right here so that you can put in the calculator a little bit nicer, this would be 8 minus 0.16t. That's the exponent, if you want to do it that way. I mean, it's just 2%. Didn't change how much I put in like I did on my other example. It's just 2%. What'd you get? Mickey's eyes got big.
4,842,431.
So you didn't change your money, right? In our other scenario, you changed your money. You doubled your money to get double the rate of return at the end, right? To double your investment at the end. But this time, it's just a simple little interest rate. The interest rate went up very small. I mean, 2%. Doesn't feel like a lot. People like to advertise 1.9% APR financing on the cars you guys buy all the time. It's 2%. It's not very much. But it's kind of hard to argue that it's not very much when you see a problem of what happens in the scenario. It's a lot. It more than doubled your amount of money just by that 2% interest rate change. It's crazy stuff. So let's change the scenario one more time. As you consider your options again, you realize that while you may not have much to invest now, and you probably don't, you should have more in the future. I mean, that's the whole reason you're in college, right? Like, your point is that when you leave here at some point, you're going to get a better job, you're going to be making more money, you're doing better for yourself. And so what you're going to do in our scenario as we adjust it now is, instead of investing $5 a week forever, you decide that every year you're going to just increase it a little bit. $2 a year more. Not a year, $2 a week more every year. So this year, right, you're investing $5 a week, but next year it's $7 a week, and then the next year it's $9 a week, and then the next year it's $11 a week. Does that make sense? Right? You're just slightly increasing it every year. There are people who do something like this with their investments all the time, where they'll increase it a percentage every year. So this year, maybe they're investing 5% of their income, but next year they're going to invest 5.5% because it's really not that noticeable to see it missing from their paycheck. And then the next year they're going to go up to 6%, right? So they change it just slightly so that it doesn't really feel painful, but it's slowly increasing over time. That's the idea here. So we're going to go back to assuming that same 14% that we did originally. Okay, so we're going back to the original premise now, that 14%, and talk about our future value equation. Now this one's a little bit different. So hang on. I didn't do this part yet. Sorry, the R of t. This R of t is a little bit different. So the first year, you're investing $5 a week, which we already said was $260, right? Yeah. But the next year, you're going to go up $2 more per week. So if you invest $2 per week, how much money is that? 104, that's right. $2 a week would be an investment of 104. So every year it's going to be 104 more than it was the previous year because it's going to go up $2 a week each time. Okay, so this is the amount that it changes every year if you're changing it $2 a week every year. Okay, so this is my R of t equation. So this right here is what's going to go back into our future value equation. So our integral goes from 0 to 50 still. But now we have 260 plus 104t. But it's e to that same point, I'm sorry, not point, 7 minus 0.14t dt. Now, we're not going to do this by hand, and the reality is that you do not have the tools to know how to do this by hand. It's not something that we would cover in a traditional calculus course. So your function 9, your math 9 in the calculator, you have to use it. You don't have a choice right now. There's no way to calculus this by hand with the tools that you've had explained at this point. But your calculator can find this for you. So if you put this into the calculator, you're just adjusting it a little bit every year. You're not going to notice it. $104 more every year. It's negligible. How much money do you have then? 7,811,168.14. $7 million. So let's actually look at what we did before, right? We said, okay, you got $2 million, you only invested $13,000, right? We're going to do the same sort of thing, and you're going to have to trust me a little bit because this is not math that is something related to our course. This is definitely a side note in terms of calculus, but the amount that you contribute each year is called an arithmetic sequence. It increases by the same amount every year. So we already kind of talked about what it does. The first year it's 260, the next year it's 104 more, right? So if I add 104, it's 364. And the next year I add 104 more, and it's 468. And the next year I add 104 more, and it's 572. And we keep doing this for the 70 years. I mean, that's what we're doing in principle. The last year would be a significant amount. It's increased over time. It's 7,540. Okay? Remember, it just changed a tiny bit at a time. You change something a tiny bit at a time, you don't feel it. That's the idea behind what's going on. The difference that's happening every time is that we add 104, right? It's called the common difference. There's an arithmetic summation formula, and you've probably not run into it. It's not outside of the ability that you could have. Sometimes it's taught in geometry courses in high school. But it actually says that you can actually find the total in an arithmetic sequence by taking 1/2 times the number of terms in your sequence. That'd be our 50 years, right? And then you have your first value, that's our 260, and your last value, that's that 7,540. Okay, so if we were to put those values in, so using this form, we know that n is equal to 50. That's what I just said. A1, the first year, was 260. And A50, the last year, was 7540. So if we find that, then our S sub 50 value, our sum after 50 years, would be 1/2 times 50 times 260 plus 7540. Like that. And it actually is a pretty good chunk of money. It's $195,000. It's a lot. I mean, there's no question that's a lot of money. But it's invested over a 50-year time span that you did that for, increasing it just a tiny bit every year. So that means that you have an investment of $195,000. but the return on your investment is 7.8 million. Right? Invest $195,000, return 7.8 million. And again, I'll say it like I did before because I think it's worth saying, if you're half wrong, you're still at almost $4 million, right? That's a lot of money. I'm pretty sure if any of you retired with $4 million, you probably would think right now, at least, that's pretty good. I did a pretty good job. You'd be pretty pleased with that. So yeah. So what will it be? $5 the vending machine, or a millionaire at 70? Did you say $5 the vending machine? Seriously, Thomas? Seriously.